Welcome to Wisdom Docs. Settle in. There is nowhere you need to be tonight, and nothing you need to solve. Let your shoulders come down from wherever they have been holding themselves all day. Let the pillow take the weight of your head, all of it, the way the sea takes the weight of a stone and never complains. The lamp can stay low. The room can stay dim. If your eyes want to close before we are very far along, let them. This is a slow story, and it will keep. You do not have to reach the end of it. You only have to drift somewhere inside it and let the quiet do the rest. I want to tell you about a slope. Not a mountainside, not a cliff, not a place that looks dangerous. A slope so gentle that if you stood on it, you would not be sure you were standing on a slope at all. Imagine the mildest ramp you have ever walked up, the kind you barely register, the kind your feet forgive without a thought. Now make it gentler than that, flatter than a wheelchair ramp, a grade of barely half a degree in places, and rarely more than 2, so soft that a marble set down on it might take a long, lazy age to decide which way to roll. On land you would call it flat. You would build on it without a second look. You would picnic on it. You would fall asleep on it in the afternoon sun and never once feel the ground tilting beneath you. And that almost flat slope, that patient, unremarkable grade, released one of the largest landslides the Earth has ever recorded. Hold those two things together for a moment, because the whole of tonight's story lives in the space between them. On one side, a slope you would not notice underfoot. On the other, a stretch of the seafloor, hundreds of kilometers wide, tearing loose and sliding away into the deep. It sounds like a contradiction. It sounds like the kind of thing that should not be able to happen, that something so slight could give birth to something so vast. But it did happen, and it happened only once in the way that mattered most, and it left behind a scar so large that we are still tracing its edges thousands of years later, still standing at the rim of it and asking the same 3 simple questions. How could this happen at all? What finally set it loose? And why do people who study the sea keep watching this same quiet ground even now? We are going to sit with those 3 questions for a long while tonight. We are not going to rush them. We are going to walk down into this mystery the way you would walk down a long, dark, familiar staircase in a house you trust, one slow step at a time. No need to see the bottom before you reach it. Let me take you there. Off the western coast of Norway, in the middle stretch of that long, folded, fjord-cut country, there is a region called Møre. And offshore from Møre, the land beneath the water does something that land beneath the water does all around the edges of the continents, though few of us ever picture it. It goes on gently for a while, a broad, shallow, shelving floor called the continental shelf, the drowned apron of the continent, where the sea is not so very deep and the light still reaches down through the green. And then, at a certain line, that shelf comes to an edge. The floor tips over and begins to descend, down and down, out of the shallows and into the true deep, into the cold black basin of the Norwegian Sea. That descending stretch is the continental slope, and the place where the shallow shelf gives way to that long descent, that great step-off at the margin of the country, has a name in Norwegian that could not be more fitting. Storegga, the great edge. Say it slowly to yourself as you lie there. Storegga, the great edge. There is something in the plainness of it, the way a coastal people who knew the sea gave the biggest thing near them the biggest, simplest name. Not a monster's name, not a name of warning, just the truth of it. The great edge, where the known shallows end and the unknown deep begins. Fishermen would have felt it in the way the water changed, in the way the bottom fell away beneath their lines, in the cold that came up from below. They named the edge, and the edge kept its name, and long after they were gone, the name was still waiting for us to understand just how much it had earned it. Because along that great edge, along the continental slope off Møre, an enormous section of the seabed once let go. We call it the Storegga Slide. And when I say enormous, I want you to feel it slowly, in pieces, the way you would take in the size of something too big to see all at once. Start with the scar. When a slope like this fails, when the material tears loose and slides away, it leaves behind a wall at the top where the ground broke free, a curved cliff called the headwall, the crown of the scar. On land, a small landslide might leave a headwall a few meters high that you could walk the length of in an afternoon. The headwall of the main Storegga Slide runs for roughly 290 kilometers along the margin. 290 kilometers. That is a wall of torn seabed, longer than many countries are wide, a single continuous crown scar you could not walk in a day, or 2 days, or many days, curving away along the edge of the deep. Imagine standing at one end of it, if you somehow could, down there in the dark and the cold, and looking along it, and knowing that the far end was further than you could travel, before you would need to rest, and rest again, and still it would go on. Now widen your eye from the scar to the whole affected floor. The area disturbed by this one collapse comes to something on the order of 95,000 square kilometers. Numbers that large slide off the mind without catching, so let me give you something to hang it on. That is roughly the size of Iceland, roughly the size of Portugal, an entire country's worth of seafloor set into motion. Not a hillside, not a valley, a nation-sized sweep of the ocean bottom, and then the volume, the sheer quantity of material that moved. The best estimates put it somewhere between 2,400 and 3,200 cubic kilometers of sediment, and people who tell this story usually round it, gently, to about 3,000 cubic kilometers. 3,000 cubic kilometers of mud and sand and clay and the debris of ice ages lifted from where it had lain and sent sliding. It is almost impossible to feel a number like that, so do not strain to. Just let it sit there, large and dark, at the bottom of your thoughts. 3,000 cubic kilometers. Enough to bury cities under a depth you could not measure by any human scale. Enough to reshape the floor of a sea. And it did not simply slump down and settle at the foot of the slope the way a little wet sand collapses at the edge of a bucket. It ran. The debris travelled outward across the deep floor, spreading, flowing, carrying itself far beyond where it began, running out as far as 800 kilometres into the deep basin of the Norwegian Sea. 800 kilometres. That is the distance of a long journey across a country, and the mud made it, out there in the lightless cold, sliding and spreading, and finally, slowly, coming to rest across a floor it had entirely rearranged. One of the largest exposed submarine landslides known anywhere on Earth. That is what lies off the coast of Møre along the Great Edge. Not a story someone made up to frighten you. A real place with a real scar that you could sail over tonight without the faintest sense of what sleeps beneath the hull. And here is the thing that will keep pulling at us as we descend, the thing I want you to carry with you like a small stone in your pocket. All of that, the 290-kilometre wall, the country-sized sweep, the 3,000 cubic kilometres, the 800-kilometre run, all of it came off a slope of barely half a degree to 2 degrees, the gentlest imaginable grade. The strange, quiet paradox at the heart of everything. The catastrophe was not born from a towering, obviously dangerous cliff. It was born from something that looked, for all the world, like flat and peaceful ground. Now let me set the moment in time, because a mystery needs its when as much as its where, and this one has a when we can name with real confidence, though it is very old. This happened about 8,150 years ago, roughly 6,150 years before the Common Era. Some tellings round it a little and say about 8,200 years ago, and either way you are in the same deep past, and I do not want you to reach for that number as a bare figure, because a bare number is a cold thing to fall asleep beside. Let me hang a picture on it instead. 8,150 years ago. Think of what the world was then. The great ice sheets that had buried the north for so long were in their long retreat, melting back, releasing the land and the water they had held. There were no cities, there was no writing, not yet, not here. Along the coasts of what we now call Norway and Scotland and the shores between them lived small bands of people, hunters and gatherers, moving with the seasons, reading the tides and the game and the weather with a closeness we can barely imagine. They lit fires on beaches that no longer exist. They gathered shellfish along shorelines the sea has since climbed over and erased. They did not know they were living on the edge of one of the largest events the seabed near them would ever produce. Why would they? It was, until the moment it was not, the most peaceful edge in the world. That is the picture to fasten to the date, not a figure on a page. A quiet coast, a low sun, a thread of wood smoke, and beneath the calm sea nearby, the great edge, holding its breath. 8,150 years ago. And how do we even know that? How can anyone stand here so many thousands of years later and say with any confidence when a piece of the seafloor let go in the dark? That itself is a small wonder, and we will come to the fuller answer as we go, but the short of it is this. The slide left traces we can date. It disturbed sediments, and it sent a wave across the sea that laid down a distinctive layer in places far from the slope, and buried in those layers are the remains of once living things, and living things carry a slow, faithful clock in the carbon of their tissues that ticks down at a rate we understand. Read the clock, and it tells you the age. Read it in many places, and the readings agree. About 8,150 years. The seabed keeps its own records, patient and unhurried, and if you learn to read them, the deep past will tell you when it moved. So we have our where and our when. The great edge off Møre in the Norwegian Sea, about 8,150 years ago. And we have our shape of the mystery. The three quiet questions that will guide the whole slow descent tonight, so let me lay them out plainly, the way you would set 3 smooth stones in a row on a windowsill. The first question. How could this happen at all? How could a slope so gentle you would not feel it underfoot ever give way on such a scale? A steep cliff failing, we understand in our bones. We have all seen the loose stone tumble, felt the instinct to step back from an edge, but nearly flat ground, releasing one of the largest landslides on Earth? That should not be possible. And yet, there is an answer, and it is one of the most quietly astonishing answers in all of geology, and it has to do with things you cannot see, with water hidden in the spaces between grains, with soft layers laid down over unimaginable stretches of time, with pressure that builds and builds where no one is looking. We will get there. Slowly, the second question. What finally set it loose? Because if the slope had grown weak over long ages, weak enough to fail, then something must have arrived at last to tip it past the edge, in a particular moment on a particular day so long ago. What was the final push after the millennia of quiet? There is an answer to this too, or at least a most favoured answer, and it involves the ground itself shaking and the frozen breath of the seabed, and we will hold that reveal for later, the way you hold the best part of a story until the listener is comfortable enough to receive it. And the third question, the one that reaches all the way into the present night. Why do people still watch this same quiet ground now? Why, so many thousands of years after it moved, do geologists keep their instruments trained on this slope and on slopes like it around the world? What is it about this old, buried event that makes it not merely a thing that happened, but a live question? An open door? That answer waits at the very end of our descent, and it will change the way you see the calm sea, gently, the way learning the name of a star changes the way you see the night. But we will not rush to it. We have a long, soft way to travel first. 3 questions. How, what set it loose? And why watch still? Let them settle. You do not need to hold them tightly. If they slip from your mind as you drift, that is perfectly all right. The story will carry them for you. Before we begin the descent in earnest, let me ask you one small, easy thing, and then I will not interrupt the quiet again for a long while. I find myself curious on nights like this about who is out there in the dark, listening, so if you feel like it, and only if it is no trouble at all. Tell me where in the world you are drifting off from tonight. Which coast, which city, which quiet room. I like to imagine the map of it, all these separate pockets of lamplight scattered across the turning world, all of us settling toward the same slow sleep. And if you are new here, if you have only just found your way to the Wisdom Docks, you are welcome to stay. Settle in with the rest of us. There is always another slow story waiting for the next night, and the one after that. That is all. Leave your comment or do not. Subscribe or do not. None of it matters more than your rest tonight. I only wanted to say hello before we go down into the dark together. Now, let me make you a promise about the shape of what is coming, so that you can loosen your grip entirely and let yourself sink. Tonight, we are going into that slope. Not quickly. Not all at once. We are going to descend into this one mystery, this single great edge off the coast of Norway, and we are going to take it apart slowly, gently, layer by layer, the way the slope itself was built up, layer by layer, over the long ages. We are not going anywhere else. We are not going to leap from disaster to disaster or pile one strange thing on top of another to keep you startled and awake. That is the opposite of what we are here for. We are going to stay with this one slope, this one sea, this one long-ago morning, and we are going to understand it so thoroughly and so calmly that by the time we reach the far end, the impossible thing will feel almost inevitable, and the fear will have turned entirely into wonder. That is the journey. One mystery, deeply, a slow walk down the great edge. So let us begin the descent properly, and let us begin where the slope itself began, not with the collapse, but with the long, patient building that came before it. Because to understand how flat ground could fail so catastrophically, you have to understand what that ground was made of, and how it came to be there, grain by grain, over a span of time that makes 8,000 years look like an afternoon. Picture the margin off Møre, the shelf and the slope, not as it is now, finished and scarred, but over the long unrolling of the ice ages. The last few 100,000 years of the North have not been steady. They have swung, slowly, between long cold spells when vast ice sheets grew and spread across Scandinavia, and warmer spells between them when the ice drew back and the land breathed out. Cold, then warm, then cold again, each cycle taking tens of thousands of years, a slow, deep tide of ice advancing and retreating across the top of the world, and each phase of that tide left its own kind of sediment along the great edge, so that the slope was built up like something layered by hand, patient course upon patient course. In the cold times, when the great ice sheet lay heavy over Scandinavia, it did not sit still. Ice flows, it grinds, it scrapes the land beneath it into powder and rubble, and carries an immense burden of ground-up rock and debris toward its edges. And where that ice reached the sea, out along the shelf, it dumped its load, a great, rapid outpouring of coarse glacial debris. Sand and gravel and rock flour piling onto the shelf edge and spilling down the slope. Fast, heavy, and abundant. Whole layers of this glaciogenic debris, the leavings of the ice, delivered to the great edge in a geological hurry whenever the cold held the land. And then, in the warmer times between, when the ice withdrew and the debris no longer poured off its melting edge, the sea along the margin grew quiet and clear, and a different, far gentler kind of sediment took over. Out in the deep water, fine particles drift down through the column, the slow, endless snow of the sea, tiny grains of clay, the remains of small living things, dust settling out of the still water. And along the margin, slow, steady bottom currents move through the deep. Patient rivers of cold water sliding along the floor, and as they move they carry and lay down their own fine, smooth deposits, sediment sorted and settled by the slow persistence of the current itself. Geologists have a name for these: contourite drifts, deposits laid by the contour following bottom currents, built up not in a rush, but over vast, calm stretches of time. Fine marine clays, soft, smooth, water-rich layers, settling grain by grain across the slope during the warm interglacial ages. So now you can see the slope for what it truly was, not a single solid thing, a layered stack, coarse, heavy glacial debris from the cold times, and between those heavy layers thin, soft, fine-grained beds of marine clay and contourite drift from the warm times. Strength and softness, interleaved, coarse upon coarse, heavy upon soft upon heavy again, built up over hundreds of thousands of years of the slow ice tide swinging back and forth. The great edge was not carved, it was assembled with a patience beyond patience, one climatic breath at a time. And here, in that layering, in that quiet alternation of the heavy and the soft, lies the first half of the answer to our first question. Because those fine, soft, water-rich beds of marine clay laid down in the warm ages, those are the weakness hidden inside the strength. They are smooth, they are slick, they hold water in the tiny spaces between their grains, and a heavy mass resting on top of a thin, soft, water-rich layer has, buried within it, a natural surface to slide along, a plane of weakness, a glide plane, waiting, softness beneath the strength, laid down so gently, over so long, by the slow snow of the deep and the patient work of the bottom currents, that no one and nothing could have marked it as dangerous. It was, quite simply, the most peaceful sediment imaginable. And it was exactly what a future catastrophe would need. Sit with that for a moment as you drift, because it is one of the tender ironies at the heart of this whole story. The very gentleness that built the slope, the slow settling in the calm, warm seas, the soft, fine clay drifting down through still water, was the same gentleness that laid the fault line for its collapse. The quiet made the weakness. The patience built the floor. Nothing violent had to happen for the danger to accumulate. It gathered, silently, in the softest layers, over ages, precisely because everything was so calm. But a soft layer alone is not enough. A slick clay bed buried in the slope is a possibility, not a certainty. For that possibility to grow into something poised on the edge of failing, something else had to happen along the great edge. And it too was slow, and it too was invisible, and it too came from the ice. Because the ice did not only leave debris, it brought weight, and it brought speed, and it is in the weight and the speed of that glacial delivery that the second half of the preconditioning hides. When the great ice sheet was funneling its ground-up burden onto the shelf edge and down the slope during the cold maxima, it was doing so quickly, piling sediment onto the margin far faster than that sediment could settle and firm and find its stability. And to understand why that speed matters so much, why fast loading is so different from slow loading, we have to go down into the smallest scale of all, into the spaces between the grains, into the hidden water that lives inside the mud. And that is where the real secret of the almost flat slope waits for us. But we will go there gently, and we will go there next, and there is no need to hold your eyes open for it. Let me tell you, before we descend into that smallest, most important space, what it is we are going to find there, so that even if you drift off along the way, the shape of it will have reached you. We are going to find that in mud like this, the strength of the whole slope does not really come from the grains themselves. It comes from how firmly the grains press against one another. And what decides how firmly they press is the water trapped in the spaces between them and the pressure that water is under. When sediment is loaded slowly, the water has time to squeeze out. The grains have time to settle down against each other, and the mass grows firm and strong and stable. But when sediment is piled on fast, faster than the water can escape, the trapped water begins to carry more and more of the load itself. The pressure of that trapped water rises, and as it rises, it does something quietly astonishing. It begins, ever so slightly, to hold the grains apart, to float them, to take the weight off the contacts between them. And a mass of mud, whose grains are being gently floated apart by the pressure of the water trapped inside it, is a mass of mud that is losing its strength, silently, invisibly, without any sign at the surface at all. That is what was happening inside the great edge, over the long cold ages, as the ice piled its burden faster than the buried clays could drain. Pressure building in the trapped water. Strength slowly bleeding away, deep down, where no eye could see it, and no instrument of that vanished world could measure it. A slope growing weaker, not because anything was pulling at it, but because of water it could not release, held under a load it could not shed. Quietly, patiently, over thousands upon thousands of years, the slope looked like flat ground. It behaved, for age upon age, like flat ground. You could have sailed over it, fished over it, lived out your whole life on the coast beside it, and died in your bed, and it would have stayed flat ground the entire time. But beneath that calm, in the soft clay beds, and the trapped water, and the slowly rising pressure between the grains, the great edge was becoming something else. Something loaded, something critical, something waiting. And we are going to go down into that waiting now, slowly, into the space between the grains, into the hidden water and the stolen strength. And we are going to understand exactly how nearly flat ground can be brought over the patience of the ice ages to the very brink of one of the largest failures the Earth has ever known. But first, let the weight of your own body sink a little further into the bed. Notice how gravity holds you, gentle and constant, the same quiet force that shaped this whole slow story, doing nothing dramatic, only pressing, only pulling, only waiting, the way it always does. There is no hurry down here in the deep of the night. The great edge waited tens of thousands of years. It can wait a few breaths more while you settle. Let your thoughts go soft at the edges now, the way the fine clay settled soft through the still warm sea. We have only just begun to descend, and already the impossible thing is beginning to make a kind of quiet sense. The flat slope, the soft hidden layers, the trapped water stealing the strength away. There is so much more still to come. The frozen breath in the seabed, the shaking that finally arrived, the slow unzipping, and then the race, the wave that crossed a sea. But all of that is further down the staircase, and we will take each step in its own good time. For now there is only this. A gentle slope off the coast of Norway, along the great edge, in the cold and the dark, growing quietly weaker beneath a calm and ordinary sea, 8,000 years ago and more, while the world above it went about its small and peaceful business, entirely unaware. Stay with me here, at the rim of it a little longer. We are going down together, slowly, into the water between the grains. The ground beneath any ocean is not a single thing. This is perhaps the first fact that needs to be understood slowly, held in the mind, until it becomes a picture rather than a phrase. Because the whole story of the great edge and what happened there depends entirely on grasping this one truth. The seabed is a record. It is a layered document of every condition that ever existed above it. Written in sediment, written in clay and sand and coarse glacial rubble, each layer recording its own particular moment in the long alternation of cold and warmth that has governed this planet's north for hundreds of thousands of years. Think of the Norwegian margin the way you might think of an old wall in a house that has stood for centuries, a wall built and rebuilt over generations, each owner adding plaster over the last, each repair laid over the crack that caused it, so that if you cut a cross-section through that wall, you would read the whole history of the house in compressed strata, thick and thin, hard and soft, each layer carrying the particular properties of its own time. The Norwegian continental margin is something like that wall, except the layers span ice ages, and the builders were glaciers, and the mortar between the courses was nothing so solid as plaster, it was marine clay, some of the finest and most water-retentive material the earth produces. For the better part of the last 500,000 years, the Scandinavian ice sheet advanced and retreated in rhythm with the slow tilts and wobbles of the planet's orbit, the same astronomical pulses that drove ice ages the world over. And each time the ice advanced, grinding south and west, pressing down onto the bedrock with enormous weight, dragging and carrying and pushing a vast load of glacial debris, it delivered that debris to the edge of the continent. At the shelf edge, at the very rim of the deep, the glaciers shed their burden. Boulders, gravel, sand, the coarse, poorly sorted rubble that glaciers characteristically leave behind. All of it dumped at the margin in what geologists call glaciogenic debris flows. Thick, fast-moving slurries of glacier-derived material that poured down the upper slope and spread across the steeper incline below, layer after layer, ice age after ice age, each glacial advance adding another course to the wall. These coarser layers were relatively strong, compressed, interlocked, with the larger grains bearing some of the load against each other. They had a kind of structural integrity, the way rough gravel packed underfoot holds firm. But between them, in the intervals between glaciations, when the ice retreated and the ocean covered the margin in relative quiet, something else accumulated. Something much finer. During the warmer interglacials, when the ice was gone and the ocean was calm and slow, the North Sea and Norwegian Sea filled with a different kind of sedimentation. Fine particles drifted down through the water column. Microorganisms lived and died and left their soft remains. And at depth, something else was at work, the slow, steady, bottom current circulation that has always moved through the deep ocean basins, driven by differences in temperature and salinity. Never fast enough to feel dramatic, but always present, always sorting and resifting the finest particles of the seafloor as it drifted along. The deposits these currents leave are called contourates, because they follow the contours of the slope, laid down in conformity with the margin's shape rather than in the random dump of a debris flow. They are extraordinarily fine-grained, they are smooth, they are rich in water. Because fine particles pack less efficiently than coarse ones and hold proportionally more pore fluid between them, and because the quiet, undisturbed deposition of the interglacial sea gave them no opportunity to compress and drain. So here is what the cross-section of the Missy margin looked like in the long period before the final Storegga Slide, alternating bands, coarse and fine, strong and soft, glacial and interglacial, layer upon layer, 10 of thousands of years of alternation. And threaded between the stronger glacial beds, those fine interglacial clays and contourates formed natural planes of weakness. Not fractures, not faults, just softness. The way a slice of hard bread with a thin spread of very soft butter between it and the next slice will shear along that butter layer before it shears anywhere else. Not because the butter is damaged, but simply because it is the weakest plane in the sandwich, the path along which force naturally flows when the system is loaded. Geologists call these the sensitive marine clay layers. Sensitive, in this context, is a technical term with a very precise and rather chilling meaning. It means that these clays, when disturbed, when their structure is shaken or their pore water pressure altered, can lose a dramatic proportion of their strength almost instantaneously. Not gradually, not slowly. A sensitive clay can go from bearing significant load to barely bearing any load at all once its internal structure is disrupted, the way a sandcastle that is firm and vertical one moment becomes a flat wet smear the next. Not because anything about the sand has fundamentally changed, but because the particular arrangement that gave it temporary strength has been undone. These clays had another property that mattered. They had been buried. And burial under the weight of subsequent deposits compresses sediment over time, normally, slowly drives out pore water, slowly increases the grain-to-grain contact that gives sediment its strength. Normally, but here, on the Møre margin, something was interfering with that normal process. During each glacial maximum, when the ice was at its greatest extent and the ice sheet was shedding enormous quantities of glaciogenic debris onto the margin, the rate of sediment delivery was extraordinary. Not just large in total volume, which it was, but large in rate. Sediment was arriving faster than the underlying layers could cope with. Fast burial is very different from slow burial. Slow burial gives the water time to drain upward through the pore spaces, to be expelled as the grains press closer together, which is how sediment properly consolidates and strengthens over time. But fast burial is like pressing a wet sponge with your palm before it has had any time to drain. The water has nowhere to go quickly enough. The pore pressure rises, and as the pore pressure rises, something crucial happens to the effective strength of the sediment. This is worth pausing on, because it is the mechanical heart of the whole story. Imagine a pile of grains. Any grains, sand, clay particles, it does not matter for the moment. Those grains bear the weight of everything above them, and they do it by pressing against each other at their points of contact, friction holding the stack in place, the way friction holds any pile of objects in equilibrium. Now imagine filling all the space between those grains with water under pressure. Not just passive water filling the gaps, but pressurized water. Water pressing outward in all directions with force. What that pressurized water does is remarkable and counterintuitive. It partially relieves the grain-to-grain contact. It pushes the grains apart, not by actually moving them, but by contributing a portion of the load that the grain contacts would otherwise have to bear. Engineers call the difference the effective stress, the portion of the total overburden weight that the grain skeleton is actually carrying once the pore water pressure's contribution is subtracted out. When effective stress falls, friction falls. When friction falls, the strength of the sediment falls. The pile does not look any different from the outside. It occupies the same space. The grains are in the same approximate positions, but the internal grip that holds the whole structure together has been quietly, invisibly diminished, in proportion to how much pressure the trapped water has built up. And on the messy margin, the trapped water had been building up for a very long time. Each glacial cycle loaded the slope faster than it could drain. Each fast-loading episode trapped more water and raised pore pressures higher than slow burial would ever have done. And when the ice retreated and the interglacial marine clays settled down over the glacial deposits, they formed a kind of cap, a fine-grained, low permeability layer that made it still harder for the water below to escape. The coarse glacial sediments were now sealed beneath fine marine clay, their pore water trapped, their effective stress reduced, their strength quietly lower than it should have been for material of their burial depth. The margin was, in this sense, systematically underconsolidated. It had been loaded faster than it had been allowed to strengthen. And the fine clay layers between the courses, those smooth, soft, water-rich contourite bands, were weaker still, because they had never been asked to bear much compressive load, had never been well drained, and were as close to their original, soft, water-saturated condition as sediment many tens of meters below the seafloor can be. The softness was not visible. The slope, seen from outside, seen from a ship passing overhead, or, if we could imagine it, from a slow descent in clear water above it, looked entirely ordinary. A gentle incline, covered in the unremarkable grey mud that covers most of the deep ocean floor. Nothing to suggest anything other than the quiet accumulation of a continental margin going about its long business. Nothing to betray the planes of weakness running horizontally through its interior, the water pressure quietly elevated above what engineering stability demands, the invisible budget of strength running, year by year and century by century, a little further into the red. How long this went on is a question answered not in years, but in ice ages. The same general process had been operating with each glacial-interglacial cycle for the better part of 500,000 years. Each cycle added new layers. Each cycle contributed new episodes of fast loading. The margin grew taller, thicker, more elaborately layered, and in certain specific intervals it grew critically weaker along those fine, smooth clay beds that had never quite consolidated the way a slowly, gently buried sediment would have. The slope that eventually failed, the slope that 8,150 years ago finally gave way, was not the product of one ice age's work, but of many, a structure of staggering geological patience, built one grain at a time over hundreds of millennia. And still it held. That is the other thing that must be said, because it matters for understanding what finally happened and why it had not happened sooner. The margin, for all its internal weakness, was in a state of fragile equilibrium. The layers were weak, but the overlying weight was distributed. The pore pressures were high, but not quite high enough. The sensitive clay films were soft, but not quite disturbed enough to lose their residual cohesion. The whole enormous, gently inclined, intricately layered structure was balanced at the very edge of its own stability, the way a tired person at the very edge of sleep holds that position for a long moment before the last tension goes and they are gone entirely. What would it take to tip that balance? Not much. This is the thing about a system that has been brought, over thousands of years, to the very threshold of its own failure. The final push does not need to be large. The margin had done the hard work for itself over time by being loaded faster than it could drain, by accumulating weak layers, by quietly raising the water pressure in its pore spaces while the world above it went about its ordinary geological business. All that remained was for something to disturb it enough, at the right moment, in the right way, something to deliver to those already weakened clay layers the brief but sufficient additional impulse that would undo their last remaining grip on the material above them. But that is the seam between two parts of this story. The first part is this one, the building, the slow, patient, invisible preconditioning of a quiet slope, the water that could not drain, the fine clay that had never fully consolidated, the pore pressure that crept upward year by year, ice age by ice age, unwitnessed, unmeasured, unfelt by any creature living on the seafloor or in the shallow waters above it. The great edge had been brought to its brink over the better part of 500,000 years, and then it waited. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And so we arrive at the other thing hiding in the sediment, the thing that is, in its own way, even more remarkable than the waterlogged clay, because at least the clay is simply material, simply wet and fine, and soft in the way that wet, fine things are soft. What was also present in those sediments, threaded through the deeper layers of the slope, was something more than waterlogged. Something that had been caught in a kind of suspended state, locked between two conditions, neither fully solid nor freely gaseous, held in precise balance by the cold and the pressure of the deep sea. Something that had no intention of staying that way forever. Methane, not drifting as a gas, not dissolved freely in the water, but frozen, crystallized into a substance that, if you held a piece of it, would look and feel remarkably like ordinary water ice, white, solid, formed into the same hexagonal cage structure that ice takes, but would not melt when you removed it from the water. It would catch fire. The substance is called a gas hydrate or methane hydrate, and it is not a rare or exotic material. It forms wherever three conditions coincide: cold enough temperatures, high enough pressures, and enough methane present in the surrounding sediment. Cold temperatures and high pressures are precisely what you find in the deep sea, below a few hundred meters of water, where the cold of the abyss presses down and the weight of the water column above provides the confining pressure. And methane in marine sediments is not rare either. It is a normal product of organic matter decomposing in the absence of oxygen, the slow bacterial processing of all the dead marine organisms that have been raining down onto the seafloor and being buried in the sediment for as long as organic life has existed in the ocean. On a continental slope like the Missy margin, organic material had been accumulating in the sediments for a very long time. Bacteria in the sediment had been breaking it down steadily, producing methane as a byproduct of that decomposition, the same process that produces marsh gas in a waterlogged field, the same slow chemical conversion that makes buried organic matter yield gas wherever conditions allow. And in the cold, deep, high-pressure environment of the Norwegian Sea, that methane, rather than rising freely as bubbles, was captured as fast as it formed, incorporated into the hydrate structure, and held there in its ice-like cage. Vast quantities of it. Not a thin film, not a trace chemical signal, but a substantial accumulation distributed through the deeper layers of the slope sediment, concentrated particularly in the upper few hundred meters below the seafloor, where conditions fell within what is called the hydrate stability zone, the specific band of temperature and pressure within which methane hydrate remains solid and stable. Within that zone, the hydrate crystals were locked into the sediment pore space the way ice is locked into frozen ground, occupying the gaps between grains, contributing to the sediment's overall structure. And the zone has a lower boundary. There is a depth below the seafloor, varying with the local temperature and pressure conditions, below which the temperatures become too warm for hydrate to remain stable even at great depth. Below that boundary, methane that encounters warmer conditions dissociates back into free gas, and it is this interface, this invisible line in the sediment where stability ends and free gas begins, that concerns geologists deeply when they think about what happened on the Møre margin. The base of the hydrate stability zone on the Norwegian continental slope runs roughly along a geological surface that can be mapped by seismic survey, a reflective boundary visible in the subsurface imaging, where the acoustic properties of the sediment change because ice, like hydrate above, is replaced by gas-saturated sediment below. And when researchers mapped this boundary in relation to the Storegga Slide, they found something that has been at the center of the debate about the slide's cause ever since. The slide plane, the actual surface along which the slope failed, the clay layer that gave way, appears to cut through or run close to the base of the hydrate stability zone. This means that in the period before the slide, conditions at the base of the hydrate zone and in the sediment just below it may have been particularly vulnerable. The base of the zone is exactly where methane transitions from solid, locked-in hydrate to free gas. Free gas in sediment pore spaces is, mechanically, even more alarming than liquid water under elevated pressure. Gas is compressible in a way liquid is not, and gas-charged sediment can lose its strength rapidly and dramatically when disturbed. Hydrate itself, when it dissociates back to free water and free gas, produces more pore fluid and gas than the solid hydrate occupied, meaning that dissociation in a confined space drives pore pressures higher still, exactly the direction already threatening the slope's stability. Now, whether hydrate dissociation was a major cause of the Storegga Slide, a minor contributing factor, or something that happened partly as a consequence of the failure rather than a driver of it, This is honestly debated among the researchers who have studied the slide most carefully. The slope's failure plane running near the base of the hydrate zone is suggestive. The general mechanism, warming post-glacial waters, rising ocean bottom temperatures as the ice age ended, shifting the stability zone upward and freeing methane at depth, is physically plausible and well understood in principle. But the exact causal weight, the degree to which this added to the pore pressure that was already elevated by glacial loading, is not settled and should not be presented as settled. What can be said with more confidence is that the slope, in the millennia after the last glacial maximum, was subject to a convergence of preconditioning processes. The rapid glacial loading of ice age cycles had built up excess pore pressures in the fine clay layers. The sensitive marine clay films between the glaciogenic courses were soft, under-consolidated, close to their failure threshold. And in the deeper layers, near the base of the hydrate stability zone, the changing conditions of the post-glacial ocean gradually warming bottom waters. Slowly rising seafloor temperatures, gradually adjusting pressure conditions as sea level itself rose with the melting of the ice, were edging the hydrate system closer to a boundary it had been comfortably far from during the deep cold of the glacial maximum. The slope was not being pushed by one force, it was being pressed from multiple directions. By the long and patient consequences of climate change, not human-caused but cosmically driven, the slow warming that followed every glacial maximum as the planet's orbit and axial tilt shifted, as the ice sheets melted and the ocean absorbed their meltwater and the bottom temperatures crept fractionally upward year by year. Everything was moving. Subtly, the stability zone boundary was adjusting. The pore pressures were elevated, the weak clay layers were waiting. The hydrate-laced sediment at depth was edging toward its own threshold, and the crust itself was moving. This is the final precondition, the one that perhaps seems most surprising when you first encounter it, that the very rock beneath the sea floor was in motion, not in the geological quick motion of an earthquake, but in the slow, decades-long rebound of a continent relieved of an enormous weight it had borne for tens of thousands of years. When a glacier stands over a landmass, its weight is not trivial. The Scandinavian ice sheet at its glacial maximum was kilometers thick, and the weight of ice kilometers thick is sufficient to depress the rock beneath it, to push the continental crust downward into the plastic mantle below, the way a mattress deforms under a heavy weight placed on it, bowing down at the center and rising slightly at the edges. This process is called glacial isostatic adjustment, and it is not instantaneous in either direction. When the load goes on, the crust takes thousands of years to sink fully. When the load comes off, the crust takes thousands of years to fully rise again, after the last glacial maximum. As the Scandinavian ice sheet retreated and thinned and finally vanished, the crust that had been depressed began to rebound. It was rising and is still rising today, in fact, though slowly now, most of the rebound having occurred in the early post-glacial period. In the millennia around 8,150 years ago, the rebound was still vigorous. The rock rising at rates geologically impressive, if geographically imperceptible, and this rising and flexing of the crust was generating stresses within the rock that could be released seismically. The crust, in other words, was cracking, adjusting, producing earthquakes, not the earthquakes of colliding tectonic plates with their characteristic violence, but the gentler and more dispersed quakes of a crust rebounding from beneath a vanished load, releasing stress as it adjusted to its new, unweighted shape. The Norwegian Sea margin, in this period, was geologically active in a quiet, structural way. And it was into this already weakened, already precariously balanced slope that at some moment around 8,150 years ago, a seismic event arrived. How large was that earthquake? The best current understanding, built from modelling the stresses that post-glacial rebound would have generated in the crust at that time and place, suggests a magnitude on the order of 7 or greater, large enough, certainly, to shake the seafloor significantly, to send pressure waves through the sediment, to deliver to those already weakened clay layers the brief, sharp, additional loading that their precarious balance could not absorb. Earthquake shaking does something specific to saturated, water-rich sediment that is already close to its failure threshold. Even a brief pulse of additional stress, even shaking that lasts only seconds, can momentarily spike the pore pressure in a sensitive clay layer beyond the point where the clay's remaining cohesion can hold. And once it goes beyond that point, even briefly, the clay loses its grip. Not partially, not temporarily. The structural arrangement that gave it residual strength, the slight bonding between the flat clay platelets, the delicate equilibrium between the grains, is disrupted, and once disrupted in a sensitive clay, it does not come back. The material suddenly is vastly weaker than it was the moment before the shaking arrived, and with that, the precondition and the trigger had found each other. The millennia of loading, the trapped water, the fine clay plains, the hydrate shifting near its boundary, the rising and flexing crust, the arriving earthquake, all of it converging at a single moment on a quiet slope off the coast of Norway, on a timeline no living thing was watching, in a depth of cold and dark where nothing marked the seconds. The seabed was about to move. What the slope did next was not what most people imagine when they hear the word landslide. It did not simply shear off all at once, the way a loose plank falls from a wall. The geology of a retrogressive submarine failure is more patient than that, even in its catastrophic moment. And the patience of it, the way the failure worked backward in stages, one block releasing the next, the slope unzipping itself in a retreat from the deep toward the rim, is the part of the story that most visitors never quite get told, and the part that perhaps best captures the strange, slow then fast character of what happened on the great edge. But that movement, the failure itself, the staging and the acceleration and the final racing debris flow, belongs to the next descent we take together. For now, the picture we have built is this. A slope of barely more than a degree or two, lying in the cold dark off the Møre coast of Norway, constructed over 500,000 years of ice age cycles into a layered structure of strength and softness alternating, with fine marine clays and water-rich contourite sediments forming smooth plains of weakness through the otherwise coarser glacial material. A slope whose pore pressures had been quietly elevated by every fast-loading glacial episode, whose effective strength had been quietly reduced by the water it could not drain, whose deeper layers held methane in an ice-like grip that warming post-glacial waters were gently loosening. A slope that was rising, slowly, on a rebounding crust, generating stresses that eventually found release in a significant earthquake. A slope that, for all of this, had held in place for millennia, balanced on the outermost edge of its own stability, the sensitive clay layers still maintaining their last fragile grip. Until the moment they did not. And so we come to the frozen thing. It has been there all along, beneath the story, present in the sediment but not yet named, a third ingredient in the quiet chemistry of failure, something older than the pore pressure, and older even than the particular arrangement of clays that made the glide plane possible. It has been waiting in the dark of the dossier as it waited in the dark of the seabed, for the moment when the temperature and the pressure and the slow turning of the post-glacial world brought it to the edge of its own stability. Methane hydrate. The name may be unfamiliar, but the thing itself is not difficult to picture if you allow the mind a moment to settle into it. Imagine methane gas, the same gas that forms in swamps and bogs, the same gas that makes a match flame blue. But instead of rising freely through water and air, trapped, caged, locked, inside a lattice of water molecules that have organized themselves under cold enough temperatures and high enough pressure into something that looks and behaves very much like ice. Not true ice, because the water molecules here do not simply freeze in their ordinary arrangement. They build around the methane, each gas molecule enclosed in a small crystalline room of hydrogen-bonded water, the whole structure held together by the very conditions of the deep seafloor. The cold, the weight of hundreds of meters of seawater pressing down, the darkness that preserves temperature and pressure in a kind of perpetual stillness. This is what geologists call a clathrate, or more specifically a gas hydrate, and it is common in the sediments of continental margins worldwide, wherever organic material has been buried deeply enough and long enough to produce methane, and wherever the seafloor sits at the right depth and temperature for the water cage to hold. In the sediments of the Møre margin, in the layers beneath the Norwegian Sea floor, methane hydrate was present in the Storegga slope material, a distributed frozen presence woven into the sediment column at depths where the conditions of stability were met. The hydrate stability zone, as researchers call it, is not a fixed thing. It is a boundary defined by the balance between temperature and pressure, and it moves slowly in geological time, but it moves. Warm the water above a sediment column, and the base of the stability zone rises toward the seafloor. The hydrate near the bottom of its stable range begins to dissociate, to unlock, the crystalline cages breaking apart and releasing free methane gas back into the pore spaces of the sediment. It is, in a way, like ice melting, but what is released is not just water, it is gas, and gas in a pore space does something particular and important to the mechanical behavior of the material around it. It weakens it. Gas bubbles occupying pore spaces disrupt the arrangement that allows sediment grains to bear load through their contacts with each other. They contribute in their own way to the same kind of elevated pore pressure that glacial fast loading had been building for millennia above the glide plane. The sediment, already carrying the quiet burden of excess water pressure from those rapid ice age deposits, now potentially carried an additional burden from gas released at depth, a further reduction in the effective stress, a further erosion of whatever frictional strength remained in the sensitive clay layers. Whether this was a primary cause of the Storegga failure or a secondary and contributing one is a question that remains genuinely open in the literature. It is worth saying plainly, because the honest uncertainty is itself part of what makes this story worth telling carefully. Researchers examining the geometry of the slide, the exact plane along which the seabed sheared away, have noted that this surface appears to cut across the base of the hydrate stability zone, right where dissociation would be expected to occur. This is not coincidence, and it is not unnoticed. It is one of the reasons hydrate dissociation entered the Storegga story as a serious hypothesis in the first place, and it is why many researchers now hold it as a plausible contributing and preconditioning factor rather than dismissing it. But the sediment record does not preserve a snapshot of exactly which molecules were doing precisely what on the day the slope broke. What the geometry tells us is that the failure plane ran through a zone where hydrate instability was possible. What it cannot tell us, with the confidence a courtroom would require, is that this was the deciding blow. The most widely supported interpretation places hydrate dissociation alongside glacial sediment loading and excess pore pressure as part of a longer preconditioning story. A slow, patient assembly of vulnerabilities, each one modest on its own, each one quietly adding to the total. The methane was one ingredient among several in a recipe that took tens of thousands of years to prepare. And the post-glacial warming of the overlying water column was providing the heat that gradually brought that ingredient toward activation. After the last glacial maximum, the great cold peak of the Ice Age, roughly 20,000 years ago, the world's oceans began to warm as the ice retreated and the climate turned. Bottom water temperatures in the Norwegian Sea, though never warm by any ordinary measure, rose above what they had been during the glacial period. The rise was not dramatic. It did not happen in a season or a century or perhaps even a millennium, at least not in the deep. But it was real, and it was directional, and at the base of the hydrate stability zone it was doing exactly what physics predicted it would do. Slowly dissolving the lower margin of the frozen methane reservoir, freeing gas in the sediment layers at precisely the depth where the weak clay glide plane was already waiting. Quiet processes, working together, that is the theme the slope keeps returning to. And all of this was happening against a backdrop of another slow and immense process, one that was reshaping the land and the seafloor from above rather than from within. The ice sheet that had covered Scandinavia at the glacial maximum was not a small thing. It was a mountain range of frozen water, kilometers thick in places, pressing down on the crust of the earth with a weight that the rock itself responded to by flexing, by sinking, by deforming over centuries and millennia under the load. The crust is not rigid in the way a tabletop is rigid. At the timescales of geology, it behaves more like a very thick, very slow fluid. It flows, it rebounds, it adjusts. And when a weight that has been pressing on it for 20,000 years is removed, when the ice melts and the water returns to the sea, the crust does not simply spring back. It rises. Slowly, as the mantle material beneath it flows back into the space that the ice had displaced, it rises. This process is called glacial isostatic adjustment or post-glacial rebound, and it is still happening today beneath Scandinavia, still measurable by GPS receivers on Norwegian bedrock, which record the land rising by several millimeters each year, the ghost of the ice still releasing the crust from a debt incurred during the last cold period. 8,000 years ago, the rebound was faster, more energetic, the crust still in the earlier and more vigorous stages of its recovery, and a crust that is flexing and rising and adjusting to the redistribution of vast weights is a crust under stress. Stress finds release, it always does, eventually, in the rock. The mechanism is familiar. Where the crust bends or stretches or compresses unevenly, it fractures. Faults, pre-existing cracks and planes of weakness in the rock activate. Earthquakes happen. The post-glacial period in Scandinavia was seismically active in this way, as the rebounding crust worked through its adjustment, and the earthquakes associated with that rebound were not minor ones. The geological record suggests that very large earthquakes, potentially magnitude 7 or greater, occurred in Scandinavia as the ice retreated and the land rose. A magnitude 7 earthquake is not a small event. On land, a magnitude 7 has the power to topple buildings, to rupture the ground, to be felt across hundreds of kilometers. offshore on a continental slope that has already been preloaded to near its failure threshold, where pore pressure is already elevated, where weak clay layers are already carrying most of the burden they can bear, where methane hydrate at the base of its stability zone is already loosening its grip. A magnitude 7 earthquake delivers something particular. It delivers shaking. And shaking applied to a slope that is already at the edge of its own stability does not need to be prolonged or catastrophic in itself to achieve what nothing has achieved in the quiet years and centuries before. It needs only to be enough. Enough to add a brief, dynamic stress to a system that was already at the margin. Enough to cause the excess pore pressure in the buried clays to pulse upward for a moment, reducing effective stress below the threshold at which the sediment could still maintain its shear strength. Enough to disturb the delicate contact between the soft clay layers and the overlying mass resting on them, so that what had held through all the slow, patient accumulation of weakness finally let go. The earthquake is the most widely supported trigger for the Storegga failure. It is modelled rather than directly observed. The sediment record cannot preserve a seismograph trace from 8,000 years ago, but the circumstantial case is strong and the mechanism is physically coherent. A large post-glacial rebound earthquake, arriving at a slope that had been preconditioned over millennia by loading, pore pressure, weak clay layers, and possibly hydrate-related weakening, was the kind of thing that could tip the balance. And after the balance was tipped, the slope did what slopes at their failure threshold do. It moved, not all at once, and not, at first, quickly. This is the part of the story where the strangeness of undersea slope failure becomes most apparent, and where the language of everyday experience begins to need the most careful translation. Because what happened next on the Møre margin was neither the sudden cliff face collapse that the word landslide typically calls to mind, nor the patient creep of a slowly moving hillside. It was something in between, and then something faster, and the sequence of those two phases is what produced the extraordinary reach of the debris. Think of a line of dominoes, not standing upright in a row, but lying on a slope, leaning against each other, each one braced by the one ahead of it. When the first in line fails, when it loses its support and slides away, the one behind it loses the bracing it depended on and follows. And then the next, and then the next behind that. Not in a simultaneous collapse, but in a sequence, each failure propagating backward through the chain, the front edge always clearing space for the next section to follow. This is the logic of retrogressive slope failure, and it is what the evidence from the Storegga headwall, that long, curved scar stretching nearly 300 kilometers along the margin, suggests happened here. The collapse did not begin at the rim and shear downward in one movement. It began somewhere lower, closer to the toe, where the critical combination of weakness and overburden first exceeded the threshold. A section of slope broke away and slid, and as it did, it removed the support that the section behind it had been depending on. That section, now unsupported on its downslope side, found itself in a configuration where its own pore pressure and weak clay layers were no longer balanced by the buttressing of the material ahead. It, too, failed, broke away, slid, and so the failure retreated. Headward, up the slope, toward the shallower water, toward the shelf edge, moving against the direction of the slide itself, the zone of collapse propagating backward even as the debris flowed forward and down. Block by block, or slab by slab, the precise geometry of individual failure units is hard to reconstruct across an area of 95,000 square kilometers. But the pattern recorded in the morphology of the scar is consistent with this retrogressive character. The slope unzipping itself in the unhurried but inexorable logic of sequential failure. Each stage of this was, in its own moment, enormous. Each slab or block that released may have been kilometers across, tens of meters thick. A volume of sediment that on land would have made a headline for a century. But in the ocean, in the darkness and the cold, it happened without sound reaching any shore, without any surface disturbance a human eye could have read for what it was, the slope expressing its failure in the only medium available to it. The slow, cold language of displaced water and moving sediment. At some point, however, the character of the movement changed. Sediment that has sheared loose from its glide plane and begun to move does not necessarily remain in coherent blocks. Depending on its composition and the conditions of its failure, it can begin to disaggregate, to break apart, to mix with the seawater that now has access to it along the failure surfaces, to transform from a solid block into something more fluid. Marine sediments, and particularly the water-rich sensitive clays that formed the glide planes here, are susceptible to this transformation. When the structure that has been holding their water in place is disrupted by shearing, they can lose much of their remaining strength very rapidly. They can remold, and remolded, water-saturated clay is not a solid that slides, it is a slurry that flows. This transition from a slow retrogressive failure of coherent blocks to a fast-moving flow of disaggregated debris is the slow motion then racing character that the structure of this story has been building toward. The early stages were the patient ones, the collapse working its way backward along the slope in the sequential logic of dominoes. But the material that had already broken free and began to mix and remold, acquiring the fluid behavior of a dense underwater current, was obeying a different physics. It was accelerating. A turbidity current, a dense, sediment-laden flow that moves along the ocean floor like an underwater avalanche, is governed by its own density relative to the clear water above it. The heavier it is, the faster it can flow, and as it flows, it can entrain more sediment from the floor beneath it, growing denser still, sustaining itself, the current feeding its own momentum. The 1929 Grand Banks earthquake off the coast of Newfoundland, which triggered its own submarine slide and turbidity current, revealed this mechanism in a way that geologists have not forgotten. The current snapped transatlantic telegraph cables lying on the ocean floor, and because the times of each cable break were recorded, researchers were able to calculate the speed of the flow as it moved from cable to cable. The numbers were striking. Hundreds of kilometers from the source, the current was still moving at speeds that no walking person could outrun. The accumulated momentum of a vast density-driven flow sustaining itself across the flat abyssal plain. The Storegga debris did not move as a single cable-snapping turbidity current in exactly the same way, but the physics of density-driven acceleration applied here too. The material that had been released from the Møre margin, roughly 3,000 cubic kilometers of it, the volume of several major mountain ranges compressed into a single moving mass, began to travel across the floor of the Norwegian Sea in the directions the deep-sea topography permitted. Downslope, away from the margin, into the basin. The debris ran out as far as 800 kilometers from the source, a distance that, to put it simply, is roughly the overland distance from London to Edinburgh and back again, covered not by a river but by a moving submarine mass of sediment released all at once from a slope nearly 300 kilometers long. 800 kilometers of run-out. Pause with that for a moment. On land, a landslide that travels a kilometer or two is already a significant event. 10 kilometers of run-out is extraordinary. The Storegga debris travelled 800, a figure that reflects the combination of the volume involved, the low resistance of the deep sea floor, the fluid dynamics of the turbidity flows that carried the finer material, and the sheer momentum of that much material set in motion on a sloping surface, however gentle that surface was. The ocean floor is not frictionless, but it offers far less resistance than any land surface, and a mass the size of the Storegga release carries momentum that the absence of trees and buildings and topographic roughness allows to persist across distances that would be inconceivable for any terrestrial slide. The headwall scar that the retrogressive failure left behind, the rim of the wound, the place where the seabed had once been and was now nothing, a sheer drop into the space the departed sediment had occupied, stretched roughly 290 kilometers along the margin. To drive the length of that scar at highway speed would take several hours. It is the kind of feature that, on land, we would call a mountain range, simply because it is large enough to have its own weather. Undersea, it is a curved, dramatic escarpment in the darkness, the edge of one of the largest failures the continental margins of the earth have experienced. And the water above it had not simply waited while all of this occurred. This is the part of the story that the next descent will carry further. The wave, the crossing of the North Sea, the sand layer in the peat. But the wave began here, in the physics of the failure itself, in the moment when the sudden displacement of that much seabed transferred its energy upward through the water column. Not gently, not slowly. The movement of the seabed, even in its staged and retrogressive character, involved the rapid remobilization of enormous sediment volumes over a relatively short time, and the water above. The water that had been resting in the space the sediment now suddenly occupied, the water whose pressure boundary had just changed across an area the size of a small country, that water moved. Tsunamis are not waves in the ordinary sense. They do not form at the surface, where wind pushes against water and creates the rolling, rhythmic swells that a sailor reads. They form at the bottom, or along the entire depth of the water column, when something displaces the seafloor suddenly enough that the entire vertical stack of water above it is set in motion. The energy propagates not just along the surface, but through the full depth, and it travels outward from the source in all directions at a speed governed by the depth of the water. In the open ocean, hundreds of kilometers per hour, faster than a commercial aircraft flies. The wave is nearly invisible at sea, a modest rise and fall of the surface, perhaps half a meter or a meter high, spread across a wavelength of tens or hundreds of kilometers, unnoticed by a ship, unreadable from the air. But when that long, shallow wave, all the energy of that enormous displacement distributed along a wavelength that may be 100 kilometers from crest to crest, begins to feel the rising seafloor as it approaches a coast, something happens to it. It slows down. And as it slows, conservation of energy insists that it must rise. The wavelength compresses, and the height climbs, and the ordinary seeming swell at sea becomes, in the shallowing water near the shore, something of an entirely different character. What the coasts of Norway, Scotland, and the Shetland Islands experienced 8,150 years ago was the arrival of this transformed energy, the great displacement of the Møre margin, translated first into a wave, then into a wall of water climbing onto land. And the evidence of that arrival has been found and measured and precisely dated in the sediment that the wave left behind. But the evidence and the coasts and the sand in the peat belong to the next part of the story. Here, at the close of this movement, it is worth resting in the picture we have assembled, not of the tsunami, not yet of the consequences, but of the failure itself. Of what it actually was, stripped of any drama that does not belong to it, rendered in its true and particular character. A slope that barely tilted. A slope built from layers of glacial debris and marine clay over 500,000 years of ice cycles, its fine horizons smooth as the pages of a closed book, its pore pressures elevated by every fast-loading glacial episode into a kind of chronic, invisible tension. A reservoir of methane frozen into hydrate in the cold deep, slowly edging toward the boundary of its stability as the post-glacial ocean above it warmed degree by fraction of a degree over millennia. A crust rising on the rebound from its ice burden, flexing, stressing, finally fracturing in an earthquake large enough to shake the slope across its full extent. And then the failure. Not sudden, not all at once, but retrogressive, working backward. The slope unzipping itself along the soft clay plane, one section releasing the next, the collapse propagating headward toward the rim, even as the debris flowed seaward and down. Slow motion staging, each step in the sequence removing the support that the step behind it needed. The whole margin participating over what may have been hours rather than seconds, the blocks and slabs detaching and beginning the process of disaggregation that would transform them from solid material into a moving, density-driven flow. And then the acceleration. The turbidity current finding its momentum on the long, unobstructed floor of the Norwegian Sea, carrying 3,000 cubic kilometers of remobilized sediment 800 kilometers from the source, leaving behind a scar nearly 300 kilometers long and an affected area the size of a small country, and sending its energy upward through the water column in a wave that would not arrive at the coasts until the slope had already gone still, until the debris had already settled into its new configuration on the abyssal floor. Until the Norwegian Sea was calm again on its surface and carrying no visible sign of what had just happened in its depths. The wave was already travelling by then, already crossing the open water, already approaching the shores. And yet there is one more thing worth understanding about what the slope was carrying at the moment it gave way. One more ingredient that researchers have spent considerable effort debating, not because the answer is clean, but because the answer is not clean, and because the uncertainty itself tells you something important about how complex a structure a continental margin actually is, and how many different processes must be considered before you can say with any confidence that you understand what happened here. Buried within the sediment column, at depths and temperatures where pressure and cold conspire to trap gas in an almost crystalline form, there was methane, frozen methane, locked inside cages of water molecules, forming a substance known as a gas hydrate or methane hydrate, not quite ice, not quite gas, but something in between, stable only as long as the conditions that created it held. The hydrate stability zone on the Møre margin sits at a particular depth beneath the seafloor, a narrow band of temperature and pressure within which the frozen form holds together. Below that boundary, too warm, too low in pressure, the cages break open and the methane escapes as free gas. In the millennia after the ice melted, the deep ocean did not warm the way the surface did. The process was slow, gradual, nearly imperceptible across any single human lifetime. But across thousands of years it was measurable, and on a slope already saturated with excess pore pressure, already riding on a weak glide plane of soft marine clay, already loaded faster than it could drain. The question of whether the base of the hydrate zone was shifting, whether free gas was accumulating just below the frozen layer, whether dissociation was releasing additional pressure into sediment that had no room for more, became and remains a serious research question. The slide plane that eventually formed appears to cut across the base of the hydrate stability zone. That is not coincidence. Or at least the researchers who have mapped the slide geometry in detail are reluctant to call it coincidence. The alignment suggests a connection, suggests that the dissociation boundary mattered in some way to where the slope chose to fail, though whether hydrate breakdown was a primary driver of the collapse or a secondary contributor. A factor that added pressure to an already failing system rather than the thing that initiated failure remains genuinely contested. This is not a settled question. The honest framing is that gas hydrates were almost certainly present, that the conditions for partial dissociation existed as the post-glacial ocean slowly warmed, and that the slide geometry is consistent with hydrate influence, but that the earthquake remains the most widely accepted final trigger, the thing that translated a critically weak slope into an actively failing one. Both can be true. The slope can have been weakened by hydrate processes over centuries or millennia, its effective strength eroded by the slow accumulation of pore pressure from gas that had nowhere to go, while still requiring the sudden, violent input of seismic energy to cross from precarious stability into irreversible motion. The match does not always need a single flame. Sometimes the fire has been building in the walls for years, and what the match provides is simply the last small increment of energy a system could no longer absorb. The earthquake that provided that energy was large. Estimates, based on the scale of the failure and the mechanics of isostatic rebound, suggest a magnitude in the region of 7 or greater, significant by any measure, the kind of event that shakes a region thoroughly, and that, under ordinary circumstances on an ordinary slope, would have been absorbed without catastrophic consequence. But the Møre margin was not an ordinary slope. It had spent thousands of years approaching a threshold, loading itself with sediment faster than its drainage could manage, trapping water in its pores, accumulating the slow, quiet pressure of gas that had no release. The crust above it was rising, flexing, stressing along faults that the unloading of the ice had created or reactivated. And when the earthquake came, the slope had nothing left in reserve, nothing held. The clay gave way along the glide plane. The first section slid, and in doing so removed the lateral support from the section behind it, which then slid, and removed the support from the section behind that. Backward, headward, the failure worked its way up the margin in what the models suggest may have been a process extending over hours. Not the instantaneous rupture of a fault, not the sudden collapse of a bridge, but a slow sequential release, block after block and slab after slab, the geometry of failure propagating against the direction of motion. The margin unzipping itself from the toe toward the crown across a front of nearly 300 kilometers. It was, in its way, an almost patient catastrophe. The slope had been patient for 10,000 years. The failure that ended that patience had a patience of its own. And then the debris moved. The disaggregated material, no longer a slope, but a flow, found the gradient of the deep Norwegian Sea and accelerated. 3,000 cubic kilometers in motion across the abyssal plain, running out over distances that no surface landslide would reach, the turbidity current spreading and thinning and travelling, carrying its energy forward over the long, flat floor of the basin. Covering 800 kilometers before the momentum finally spent itself and the sediment began to settle into its new configuration, layer by layer, grain by grain, in the deep, cold dark, where the only movement now was the slow drift of deep water currents and the gradual accumulation of whatever fell from the water column above. The slope was still. The sea above it was already moving. And somewhere to the south and west, the wave the displacement had launched was crossing open water, its energy invisible at the surface, its height spreading thin across the depth of the ocean, and then rising, concentrating, as the seafloor began to shallow beneath it. A wave generated by a submarine landslide does not look, in open water, like what people imagine when they hear the word. It does not rise into a great wall of blue-green water above the surface, its crest catching light, its face vertical and dramatic and announced. In the open ocean, a tsunami is almost nothing to see. The wavelength, the distance from one crest to the next, is measured not in meters but in hundreds of kilometers, and the surface disturbance, spread across that enormous span, is only a few centimeters, or at most a meter in height. A ship at sea in the path of such a wave might not feel it at all. The energy is not at the surface. It is distributed through the entire water column, from the surface to the floor, moving as a pulse of pressure rather than as an ordinary surface ripple, and it travels in deep water. At speeds approaching 800 or 900 kilometers an hour, as fast as a jet aircraft, the whole depth of the ocean participating in the motion. This is why tsunamis are so difficult to conceive of correctly. We use the word wave, and the mind conjures something a body can outrun, something visible, something that rises and falls in a space you can measure. The wave that left the Storegga margin 8,150 years ago was none of those things. It was a pressure front crossing the Norwegian Sea, the North Sea, the North Atlantic, the energy of 3,000 cubic kilometers of sudden displacement translated into motion and spread outward in every direction from the source, diminishing with distance but not disappearing, bending and refracting as the topography of the seafloor guided it, shoaling and rising wherever the sea became shallow enough to force all that deep water energy upward into height. And where the sea became shallow, the wave became visible. It became something else entirely. Along the western coast of Norway, where the continental shelf rises from the deep Norwegian Sea, and the coast itself is a complicated geography of fjords and headlands and exposed rock shelves. The wave that arrived in the hours after the collapse was measured afterward, not by any instrument, for no instrument existed then, but by what it left behind. The physical mark of a wave is not the wave itself, but the sediment it carries, deposits it when its energy finally fails, and places it somewhere that land-based processes would never reach. Sand from the seafloor in a layer of coastal peat, gravel above a horizon of soft freshwater mud, a thin stripe of marine material inside an otherwise terrestrial sequence, sealed, preserved, waiting for 8,000 years until someone cut a section through a bog and noticed the anomaly. Along the Norwegian coast, those layers record water that climbed roughly 10 to 12 meters above the sea level of that time. 10 to 12 meters. That is the height of a 3-story or 4-story building, the wave arriving not as a moving surface, but as a rising flood. coming in fast and continuing to rise, the water pushing inland through every low passage, up every valley that opened to the sea, over every beach and low headland, carrying whatever it found, and then releasing it when the energy finally ran out and the water began, over the course of minutes or tens of minutes, to pull back. In the Shetland Islands, which lie north of the Scottish mainland and east of the Faroe Islands, the geometry of the waves' approach and the local bathymetry, the shape of the shallow seafloor around the islands, amplified the run up to something the Norwegian coast did not see. The estimates for Shetland reach roughly 20 to 25 metres. That is not 3 or 4 stories. That is a 7-story or 8-story building, a wave that climbed higher than most of the structures that exist in those islands today, that swept across ground that is not particularly low-lying, that left its sand layer in places that by any ordinary reckoning should be out of the sea's reach entirely. The sand is there. It was found. The numbers that come from measuring how high and how far inland it runs are difficult to accept even when you understand the mechanism that produced them, even when you have walked through the physics step by step and arrived at the figure with full understanding of how it was derived. 25 metres of wave climbing a Shetland hillside 8,000 years ago. To the south, where the wave crossed the open North Sea toward the coastlines of Scotland and England, the depths are shallower and the distances shorter, and the signal that reached those shores was attenuated, smaller than what Shetland received, larger than what an ordinary storm would leave. The sand layers in Scotland record run up of roughly 3 to 6 metres along the eastern coast. 3 to 6 metres is still a wall of fast-moving water arriving with no warning across a coast inhabited by Mesolithic people who had lived beside this sea all their lives and had no reason to expect what was coming. It is enough water to move through a landscape with great violence. It is enough to carry sediment far inland, up the narrowing channels of river mouths and estuaries, depositing its cargo of marine sand tens of kilometres from the open coast. The Firth of Forth, the long inlet that reaches inland from the eastern coast of Scotland, carries that sand. The Montrose Basin, the tidal lagoon and estuary on the Angus coast further north, carries it too. These are places where the wave's signature has been found in detail, in cores pulled from the sediment beneath the intertidal zones. The mud and peat sequences read like a very slow book in which each layer is a year or a decade or a century, and suddenly, in the middle of an otherwise quiet sequence of dark peat laid down by the slow accumulation of marsh plants, there is a layer of pale marine sand, out of place, too coarse and too salty for the environment it is buried in. And then the peat resumes above it as if nothing had happened, the marsh returning over the years to the surface the wave had briefly claimed. This is the fingerprint. This is how geologists know not only that the wave happened, but where it went. The sand sheet is a physical object distributed across a geography, and the shape of that distribution, which bays received the thickest deposit, which headlands seem to have blocked or focused the flow, how far inland the grains travelled up each estuary, all of that information is encoded in the sediment and has been read layer by painstaking layer over decades of research. The wave did not stop at Scotland. The same physics that carried it there carried it outward in every direction from the source, across the full breadth of the North Atlantic, diminishing as the energy spread over ever greater distances, but not disappearing until the ocean floor and coastlines had absorbed it all. The Faroe Islands, halfway between Norway and Iceland, carry the sand layer. Iceland itself has deposits that have been connected to the Storegga event, and northeastern Greenland, across the full width of the North Atlantic, from the margin that collapsed, has yielded evidence of the wave's arrival. A signal so attenuated by distance that it is barely there. A faint trace in the coastal sediment record, but there nonetheless. The wave reached Greenland. It crossed an ocean. The energy released by the failure of a continental slope off Norway was sufficient, in this attenuated, spreading form, to leave a physical mark on the icebound coast of Greenland. That reach is part of what makes Storegga the reference case for submarine landslide tsunami hazard. Not just the size of the slide, not just the height of the wave in Shetland, but the geographical extent of the signature, the way a single event on a single continental margin left its mark from Greenland to the Faroes to Iceland to Scotland to Norway, a net of evidence spread across the Northern Ocean that, once you know what to look for, you can find in core after core and section after section the same thin pale sand repeated at the same stratigraphic horizon. 8,150 years old, across the whole North Atlantic world. There were people in that world. This is worth pausing on and worth holding carefully without overclaiming. The time was the Mesolithic, the Middle Stone Age, the long period of European prehistory after the ice retreated and before agriculture arrived from the southeast to change the continent's way of life. The people of the North Sea region were hunter-gatherers, skilled and mobile, following reindeer and red deer and aurochs across a landscape that was still changing rapidly as the climate warmed, the ice melted and the sea rose. They fished. They gathered shellfish. They moved along coastlines that were themselves moving, the sea claiming a little more low ground every generation. The familiar estuaries of a parent's childhood silted and altered by the time a child was grown. And below those coastlines, in what is now the bed of the southern North Sea, there was land. Doggerland, the name was given by geologists working centuries after the fact, taking it from the Doggerbank, the shallow sandbank that still rises toward the surface in the central North Sea, and that preserves in its shallow contours a memory of the land that was once above the water here. Doggerland was a low-lying plain, partially drained by rivers that now flow under the sea, its topography shaped by the glacial processes of the last ice age, its surface covered in the vegetation of a cool, wet northern landscape. It had been inhabited. Hunting tools and animal bones have come up in fishing nets from the seabed. A piece of worked bone, the antler of a red deer shaped by human hands, dredged from under the North Sea and dated to this period. Fragments of the world that drowned. By 8,150 years ago, Doggerland was already in serious retreat. The sea had been rising since the end of the last glacial maximum, roughly 18,000 years before, and the rate of rise had been fastest during the periods of most rapid ice melting. In the millennia before the Storegga event, the sea had already claimed much of what Doggerland had been at its greatest extent, and what remained was lower, narrower, more fragmented. A landscape that was becoming an archipelago, then a sandbar, then nothing. The process was slow enough that no individual generation would have watched Doggerland disappear in the way a person might watch a flood. It was slow in the way that the building of a continental margin is slow, grain by grain and generation by generation, imperceptible within a human life, but enormous over centuries. The Storegga tsunami arrived into this already retreating world. What it did there is genuinely debated, and it is important to hold the debate honestly. The wave swept across the shallows of the remaining Doggerland coast, across whatever beaches and low headlands and river mouths still connected Britain to the continent across the southern North Sea. where the water was very shallow. Even a wave with modest energy remaining at this distance could travel far inland and deposit sediment across areas that the sea had not yet claimed by its slow rise. The wave was not the agent that drowned Doggerland. The sea level rise was doing that on its own, over millennia, and would have completed the task with or without Storegga. But the wave may have delivered a sudden, violent version of something the slow rise had been doing gently. It may have rushed over ground that the sea would not have reached for another generation or two, stranding people on what had been dry land, altering the coastline in hours in ways that would otherwise have taken years. Whether it hastened the final separation of Britain from the continent by a meaningful interval, or whether the sea level rise had already done enough that Storegga's contribution was marginal, is a question the sediment record has not yet fully resolved. What can be said is that the people who lived on these coasts and in these lowlands experienced a wave they had no framework to understand, arriving on a day that may have begun like any other day in that long northern summer or autumn, and that the wave left behind it a changed coastline. Some of them almost certainly did not survive it. How many, and where they were standing, and what they made of what they saw before the water came, none of that is in the record. The sand layer is what remains. The sand layer and the silence above it, the peat growing back over the disrupted surface, the marsh returning, the Mesolithic world continuing in the people and places the wave did not reach. It is worth sitting with that silence for a moment before moving forward. The margin off Møre did not rest after the collapse. It never does. A continental margin is not a structure that fails once and remains empty. The same processes that built the sediment package that failed 8,150 years ago began again immediately after the failure. In the most literal sense, the rivers of Scandinavia continued to deliver sediment to the shelf edge. The bottom currents continued to lay down their fine contourite drifts. The biological rain of particles from the surface ocean continued to settle onto the disturbed seabed. The scar began to fill. Slowly, patiently, over the millennia since the collapse, the slope has been rebuilding. This is not unique to Storegga. Examination of the stratigraphy beneath the slide scar reveals that the main event 8,150 years ago was not the first time this margin had failed at scale. The geological record shows evidence of very large slides on roughly the same margin extending back over at least the last 500,000 years, their recurrence loosely tied to the rhythm of glacial cycles. The Great Ice Age oscillations that repeat on timescales of roughly 100,000 years, each glacial maximum loading the slope with fast deposited sediment, and each deglaciation removing the ice load, rebounding the crust, and warming the ocean bottom waters toward the conditions that could destabilize the hydrates and tip the weakened slope past failure. The margin has done this before. It will, on geological time, be capable of doing it again. The question of when and whether the present configuration of sediment and pore pressure and hydrate stability is anywhere near the threshold that would make failure possible in any timescale a human civilization would care about is exactly the question that has driven the most intensive scientific study this margin has ever received. The reason that study happened when it did is not purely scientific curiosity. It is a gas field, Ormenlang. The name translates roughly as the long serpent, taken from a medieval Norwegian poem, and the field lies in 800 to 1,100 meters of water, inside the slide scar itself, in the very sediment that was disturbed and partially emptied by the Storegga collapse. It was discovered in the late 20th century and developed in the 2000s, and it is one of Norway's largest gas fields, an important energy source for the Norwegian economy and for gas supplies to Western Europe. The infrastructure that extracts that gas sits on the floor of the Storegga Slide. The pipelines that carry the gas ashore cross the continental margin that once failed catastrophically. The question of whether anything like that failure could happen again, on what timescale, under what conditions, triggered by what mechanism, was therefore not abstract when the development of Ormen Lange was being planned. It was an engineering question with very large financial and safety implications. The response was a geohazard research program of unusual depth and funding. Sediment cores were taken across the margin in detail that would not have been financially possible in purely academic research. High-resolution sonar surveys mapped the morphology of the scar and the adjacent unfailed slopes with a precision that revealed structures invisible in earlier surveys. The weak layers, the sensitive marine clays that had formed the glide planes, were sampled, brought to the surface and tested for their mechanical properties in laboratory conditions. The distribution and stability of gas hydrate in the sediment column was mapped as carefully as the technology of the time permitted. The history of pore pressure and sediment loading was reconstructed from the stratigraphy. All of this work, driven by the practical needs of safe field development, produced the scientific foundation on which the modern understanding of the Storegga Slide rests. The conclusion, as of the research that emerged from this period, was that the present-day sediment on the unfailed portions of the margin is not in the same condition as the sediment was immediately before the 8,000-year-ago event. The loading, the pore pressure, the hydrate configuration, these are not yet in a state that would make a failure of comparable scale imminent in any human sense of that word. The slope has not rebuilt to the point of criticality, but the slope is rebuilding. And the question of whether the conditions that produced Storegga could reproduce themselves on a margin that has been doing this, roughly and loosely, on a glacial cycle cadence for at least 500,000 years, is a question that honest science does not answer with a simple no. Storegga is not alone in what it represents. Other margins, other slopes, other events give the same phenomenon different faces, and each adds a piece to the understanding of how submarine landslides work and how fast their consequences move. In 1929, off the coast of Newfoundland, an earthquake with a magnitude somewhere in the range of magnitude 7 struck the continental slope at a feature called the Grand Banks. The shaking destabilized sediment on a slope that, like the Storegga margin, had been loaded with material delivered by glacial processes. The slide generated a turbidity current, a dense, fast-moving avalanche of water and sediment that moved down the slope and across the abyssal plain of the North Atlantic at speeds that have been estimated at up to 90 kilometers per hour in the steepest sections, slowing as the gradient gentled but remaining fast and powerful enough to snap the transatlantic telegraph cables that crossed the seafloor there. The cables broke in sequence, each break recorded with a timestamp at the receiving stations on shore, and from those timestamps the speed of the flow was calculated after the fact. It was one of the first direct demonstrations that submarine flows are not the slow, stately creep that many had imagined, that they move with a speed and force capable of destroying engineering infrastructure on the seafloor. A tsunami followed, reaching the Newfoundland coast and killing 28 people, modest in the scale of Storegga's wave, but real and fatal and close enough to recorded history that survivors gave testimony about what they had seen. In 1979, at Nice, on the French Mediterranean coast, a slope at the edge of a harbour construction project failed during a period of heavy rain and river discharge that had rapidly loaded new sediment onto the submerged face. The failure was small by Storegga's measure, incomparably small, but it generated a local wave and damaged harbour infrastructure and demonstrated that coastal and submarine slopes can fail suddenly and without warning when sediment is delivered faster than it can stabilise. A gentle gradient made suddenly unstable by rapid loading. The same principle, at a scale a city harbour makes comprehensible. In 1998, in Papua New Guinea, a submarine slump triggered by an earthquake generated a tsunami that arrived on the north coast of the island with almost no warning and killed more than 2,000 people. The slump was small, the tsunami was devastating. The distance from source to shore was short, the warning time effectively zero, and the death toll was entirely from the wave, which in places exceeded 10 metres of run-up on a coast, where 10 metres of fast-moving water arriving in the middle of the night is not something you survive without either very good luck or very early warning. Papua New Guinea, 1998, became a reference case for the tsunami hazard specifically from submarine slumps rather than from the tectonic earthquakes that most tsunami warning systems were designed to detect, and it changed how researchers thought about the relationship between slide size and wave size. A relatively small slump in the right geometry, close enough to shore, can produce a wave that a very large distant earthquake would be proud of. These events are not Storegga. None of them are Storegga. But each of them is a facet of the same phenomenon, the continental margin as a structure that stores energy and releases it, the slope as an interface between the solid earth and the ocean that is more dynamic, more hazardous, and more capable of sudden failure than its quiet surface suggests. Grand Banks showed how fast the flows move. Nice showed how quickly loading can tip a slope past its limit. Papua New Guinea showed that a small slump and a short distance can produce a wave that kills thousands in minutes. Storegga showed what all of these processes look like when they operate at the largest possible scale, across nearly 300 kilometers of margin, with 3,000 cubic kilometers of material and an ocean to cross. And now the ocean is warming. The bottom waters of the world's ocean are not warming at the same rate or with the same magnitude as the surface. Deep water is insulated from surface change by the sheer volume of cold water above and below, and the circulation that refreshes the deep ocean has its own timescales, measured in centuries and millennia rather than years. But the deep ocean is not static. It has warmed measurably in the past decades, and the trend, under the range of projections that current climate science considers plausible, continues, and the relevance of that warming to the stability of continental margins is not abstract. It is direct. It runs through the methane hydrate, the gas hydrate that lies buried in the sediment of continental margins around the world, is stable within a zone defined by temperature and pressure. Cold temperatures and high pressures, the conditions of deep water sediment, favour the hydrate cage, the ice-like structure that traps methane molecules and holds them in solid form within the sediment. Warmer temperatures or lower pressures push the equilibrium the other way, destabilizing the cage and releasing the methane as free gas. The boundary between the stable and unstable zones, the base of the hydrate stability zone, is not fixed. It moves in response to temperature. As bottom waters warm, the base of the hydrate stability zone migrates downward into sediment that was previously in the stable zone but is now not, and methane that was locked in solid form begins to dissociate. In the Storegga sediment, the slide plane, the surface along which the failed mass slipped, has been found to cut across the base of the hydrate stability zone. Whether the hydrate dissociation there was cause or coincidence or a contributing factor among several others remains genuinely uncertain, as has been said throughout this account. But the geometry is significant. The zone of weakness that the slope failed along corresponds to the zone of hydrate instability, and in the conditions that prevailed after the last glaciation, warming bottom waters. Rising seafloor temperatures as the ice retreated, the hydrate at that boundary was already under stress. This is not a scenario unique to Storegga. Margins around the world carry gas, charged sediment. Many of them are in shallower water than the Norwegian Sea, where the hydrate stability zone is thinner and its base closer to the seafloor, which means that warming reaches the base more quickly. Many of them have been loaded rapidly by glacial or river-derived sediment and have the same structural preconditions: the excess pore pressure, the fine-grained glide planes, the over-steepened, under-drained stratigraphy that characterized the Møre margin before 8,150 years ago. None of them is Storegga. None of them is demonstrably at the same condition of criticality that the Storegga margin had reached by the time the earthquake came. But geologists who study continental slope stability watch these margins and their hydrate systems with the same careful, patient attention that the Norwegian Sea research applied to Storegga itself. The watching is not panic. It is not prediction. It is the practice of paying attention to a system that is slow enough to appear static, but has demonstrated in the geological record that it can release its stored energy in ways that are rapid, large, and far-reaching. The watching is what you do when you understand the mechanism well enough to know what the warning signs would look like. And when you also understand that the mechanism operates on timescales that can outrun the patience of any individual researcher or any single generation of instruments. You deploy the instruments, and you maintain them, and you read what they send back, and you update the model, year by year, the way the sediment builds, year by year, on the slope above the scar. This is what 8,000 years of accumulated knowledge looks like in practice. Not certainty. Not prediction. A margin studied and watched and understood well enough that if its pore pressures began to rise, or its hydrates began to destabilize, or its sediment began to show the first signs of creep, there would be instruments to see it, and scientists trained to read what those instruments said. The slope off Møre is quiet now. The scar is there, 300 kilometers of torn margin visible in every high-resolution survey. The smooth walls where the sediment tore away, and the hummocked, chaotic debris field on the deep abyssal plain where the material came to rest, 800 kilometers from where it started. The gas field inside the scar produces its gas, and the pipelines carry it to shore, and the instruments on the seafloor measure what they measure, and the data comes back, and the models are updated, and the quiet continues. But the quiet is not nothing. The quiet is the same thing the slope was doing for 10,000 years before the earthquake came, accumulating, loading, draining imperfectly, building the invisible conditions that it was building, one grain and one season at a time. The quiet on a continental margin is not stillness. It is a very slow process that has occasionally, over the half-billion-year history of ocean margins, been interrupted by something very fast and very large and very far-reaching. What makes Storegga worth knowing, worth spending a long night inside, is not the wave. The wave is impressive, and the run-up figures for Shetland are genuinely astonishing, But a wave, even a wave that crossed the North Atlantic and left its sand in the peat of Greenland, is a consequence. It is the output. What makes Storegga worth knowing is the input, the gentleness, the barely there gradient, the 0.5 degree to 2 degrees of incline across which 3,000 cubic kilometers of seabed built its slow, invisible tension, grain by grain and ice age by ice age, until a single earthquake, one moment of shaking that lasted perhaps a minute or two in the long silence of geological time, was enough to set the first block loose and begin the backward unzipping that ended with a wave. Crossing an ocean. The world is full of slopes. Most of them are quiet. The continental margins of every ocean on the planet are piled with sediment and crossed by slow bottom currents, and threaded with the frozen methane of 1,000 ancient accumulations. And the vast majority of those slopes will never fail in any timescale that matters to the civilization building its infrastructure and livelihoods along the coasts above them. The geological record is not an endless catalogue of Storeggas. It is a long, mostly undisturbed sequence of slow accumulation, punctuated very rarely by events of this scale. But very rarely, over 500,000 years, is not never. And the slopes are not aware of the time scale that matters to us. They are aware only of pressure and strength and the slow physics of water and weight and grain and temperature, and they will continue to respond to those things on their own schedule, as they have always done. The sand layer in the peat is still there. Under the Shetland hillside, under the edge of a Scottish estuary, under the surface of a Faroes coastal deposit, under the sediment of a Greenlandic bay. You could go there with a core tube and push it into the sediment and pull it back up and look at the sequence and find the layer, the thin, pale marine sand in the dark peat. And hold in your hand the physical record of a morning 8,150 years ago, when the sea arrived where it had no business being, and then receded and left this mark behind. The mark is quieter than the event it records. That is always the way with these things. The catastrophe makes the noise, the sediment makes the record. And the record is what endures, patient and dark and cold and precise, waiting in the earth for whoever comes along with the instruments and the curiosity to read it. The Norwegian Sea is dark tonight. The slope off Møre is covered by 800 meters of cold water, and the water is still, or nearly still, the slow, deep circulation of the North Atlantic moving through it in the unhurried way that deep water moves, carrying its cargo of cold and dissolved oxygen from the polar regions toward the equator, and back again on timescales no person has ever lived long enough to witness in full. The scar is there in the dark, the torn margin, the smooth walls and the hummocked plain, and the slow, grain by grain rebuilding of what fell. The gas field hums its quiet work, the instruments measure, and the slope is patient, as it has always been patient. As patience is the one quality that continental margins have in abundance, the one thing they can offer in quantities that dwarf everything we might imagine when we try to picture geological time. Something enormously large came from something almost imperceptibly gentle. That is the mystery of this place, and it does not resolve into something comfortable or frightening or certain. It resolves into wonder, the specific, grounded, evidence-anchored wonder of understanding a mechanism and still finding it almost impossible to hold in the mind all at once. The 2 degrees of slope and the 3,000 cubic kilometers of debris, and the wave in the Shetland peat, and the sand on the Greenland shore, and the quiet seafloor instruments measuring. Tonight, what the quiet margin does. If you have been following this account from the beginning, you have now travelled the whole arc of it, from the cold open on a slope too gentle to see, through the millennia of invisible loading and the frozen methane and the earthquake and the slow backward collapse and the racing debris and the wave, to the sand in the peat and the scar being studied and the warming ocean and the vigil still being kept. The question the title asks, how a quiet Norwegian slope became one of Earth's largest landslides, has an answer now, and the answer is patient and specific and strange, and it ends not with resolution, but with a margin that is building again, quietly, in the dark. You have done enough for one night. Put down whatever remains of the day. The Norwegian Sea is cold and far away, and 8,000 years deep in its mystery, and everything that can be known about what happened there has been laid out carefully, and the rest is the honest open question of what the slope is becoming, grain by grain, in the years that neither you nor I will live to see the end of. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. There are more stories here of the same slow and careful kind, waiting for whenever you want them. Tie off here at the Wisdom Docks. The tide will wait till morning.